Welcome to lecture 5.3, Why RSA Works. By RSA, of course, I mean the RSA cryptosystem, and I assume that if you're watching this lecture, you have either watched the prior lecture in this series, or you are already familiar with RSA. Okay, let's get started. Recall that the first step of the RSA algorithm is for the message recipient to choose two large prime numbers, P and Q, and multiply them together. And then the recipient is free to share this product n, but has to keep P and Q private. And the idea being is that factoring a large number into primes is a computationally difficult problem and completely infeasible if the primes are several hundred digits in length. In practice, this is basically done by guess and check. So we pick a large 200-digit number and check to see whether it's prime. So the guess is easy to see how it works, but the checking part is non-trivial. And we will learn both why this works, but also how it works in this lecture. And to do that, we will need a little bit of number theory. We'll start with the prime number theorem. And this says the probability that a random number n is prime is approximately 1 divided by the natural log of n. And I should clarify that this is assuming that n is large. So for small n, this is not a very good approximation, but as n gets larger and larger, it actually does approach this probability asymptotically. And of course, this probability approaches 0. But we can still use it for any finite n, and it's pretty accurate. Said differently, the limit as n goes to infinity of the proportion of numbers less than n that are prime minus 1 divided by the natural log of n, and I should make sure I put the parentheses here, is equal to 0. I think I'm going to show you one more way to state the prime number theorem, and this is probably the most common. And I'm doing this just because you never know which one of these is going to stick out the most. So if we define pi of n to be the function that counts how many primes there are up to n, so this is formally the number of integers less than or equal to n that are prime, then this number grows asymptotically with n over the natural log of n. So I could state this in terms of limits. That means if you take this quantity and divide it by that quantity, then the limit as n goes to infinity of that proportion is 1. But I think I'll just leave it like this. Why we care about this for cryptography is that it tells us that the chances of a random 9-digit number being prime is approximately 4%, so 1 in 25. For a 200-digit number, it's approximately 0.2%, in other words, 1 in 500. This is useful because it gives us a heuristic for finding a large prime, which is what we need for RSA. We begin with an infinite loop. It's this while true. And we let n be a random 200-digit number. It's easy for a computer to generate one of these. If n is prime, then we return n and we break out of the loop. Due to the prime number theorem, we expect that this will loop for approximately 500 times, more or less. Of course, this just being the mean of a distribution means it could be twice that many if we get unlucky, but it's not going to be orders of magnitude more. And that's really all we care about. It's something that a computer can easily handle. Now that said, what I haven't yet dealt with is this line here, if n is prime, namely, how do we check whether a number is prime? If n is small, that's easy, but what about a 200-digit number? We know that it's computationally infeasible to factor it. That's why RSA works in the first place. So is there a quick and dirty trick that will tell us, so we don't need a factor, we just need to know, is there a divisor? So how do we check this efficiently for such a large number? That's what we'll do next. To check whether a large number is prime, we use something called the Fermat Primality Test. And this is a probabilistic method. And it doesn't actually check whether a number is prime, but it checks whether a number is probably prime. And I'll explain that shortly. It relies on the following result, which we'll prove on the next slide. For now, I just want to state it here and then say a few words about it, especially how it relates to the Fermat Primality Test. So this is called Mazlow Theorem. It was due to Pierre Fermat, a French mathematician, I want to say in about 1640. He, like many of his results, he did not prove this, he just wrote it down, and I think Euler proved it almost 100 years later. This is not to be confused with Fermat's last theorem, which was that famous theorem that was unsolved until Andrew Wiles proved it in the 1990s. So Fermat's little theorem says that for any prime p and integer a, that a to the p is equivalent to a modulo p. Let's do a couple of examples just to get warmed up to this. Let's first assume a is equal to 2 and p is equal to 5. Then 2 to the 5th. Of course, we're going to do mod 5. So 2 to the 5th is 32, which is 2 mod 5. So that checks out. Now let's see what happens if we switch a and p. So suppose p equals 2 and a equals 5. So everything we're doing here is mod 2. So first of all, in that case, we really can reduce a down to 1, mod 2. Hold on for that thought for a moment. But let's just continue with this. 5 squared is 25, which is certainly equivalent to 5 mod 2, because that's equivalent to 1 mod 2. So this checks out, although we can see that it doesn't really make sense to do this when a is bigger than p, because we could always, because we're working mod p, so why not just reduce a to be less than or equal to p? And that's what we'll do. Without loss of generality, we will assume that a is an integer between 0 and p minus 1 inclusive. Again, it still works for any other a, but there's no reason to pick an a that's larger than this. First of all, if a is 0, then this result trivially holds, right? 0 to the p is equivalent to 0 mod p. So we are going to prove this on the next slide, and we can disregard the case when a equals 0. So we can just assume that a is between 1 and p minus 1. Assuming that a is non-zero, we get that the GCD of a and p is equal to 1, right? Because p is prime and a is a positive integer less than p. Because of this, a has a multiplicative inverse mod p. In other words, we could solve ax is equivalent to 1 mod p. Remember, we saw in a previous lecture how to do this using the extended Euclidean algorithm. So in other words, we can find an x and a y so that ax plus py equals the GCD of a and p, which is 1. And then if we take this entire thing and we reduce it, mod p, Then this term goes away, and we get that AX is equivalent to 1 mod P. I'm going off on a little bit of a tangent. We don't have to worry about how to actually compute A inverse. Let's just assume that it exists. And let's take our original equation in Fermat's little theorem and multiply A inverse on both sides. And we get A to the P minus 1 is equivalent to 1 mod P. We now have a heuristic for testing primes. And here's how it goes. Given a natural number n, compute A to the n minus 1 mod n for many random values of A less than n. If for some value of A, we just need 1, A to the n minus 1 is not equivalent to 1 mod n, then we know that n must be composite. This is what we call a no certificate for primality. Unfortunately, there's no such thing as a yes certificate for this primality test. In other words, if A to the n minus 1 is equivalent to 1 mod n, for every A that we try, we can't promise that n is prime. The best we can say is that it is probably prime. So what does that mean, and how probable is it? That's what we need to talk about. But before we do, I want to take a few minutes to prove Fermat's little theorem, and then we'll come back to this issue. Recall from the previous slide that Fermat's little theorem is that A to the P is equivalent to A mod P. And we quickly notice that this is trivial if A is 0 mod P. In other words, if it's a multiple of P. So because of that, we can disregard that case and state Fermat's little theorem as follows. For any prime P and integer A that's relatively prime to P, A to the P minus 1 is equivalent to 1 mod P. We also showed this version on the previous slide. Okay, so let's prove this. Recall, as we said before, that we can assume without loss of generality that A is a positive integer less than P. Consider the following list of numbers: A, 2A, 3A, 4A, all the way up to P minus 1 times A. I claim that no two of these are equivalent modulo P. In other words, on this list, exactly one of these is 1 mod P, one of them is 2 mod P, one is 3 mod P, all the way up to P minus 1 mod P. Let me give you a bit of a preview as to where we are going with this. So if we take this list of numbers, we multiply them all together, modulo P, then we get 1 times 2 times 3 times all the way up to P minus 1, which is P minus 1 factorial mod P. And P does not divide P minus 1 factorial, clearly. Okay, let's continue. But let's first see why no two of these are equivalent mod P. And it's actually a very simple argument. Suppose that two of them were. Suppose that Ka is equivalent to La mod P. Then we can multiply both sides of this equation by the multiplicative inverse of A to get that K is equivalent to L mod P. Thus, the product of this list of numbers from above, there's two ways to write it. One of them is A times 2A times 3A all the way up to P minus 1A, which, by the way, notice this is, we have P minus 1 copies of A times P minus 1 factorial. And we also know that mod P, this is equivalent to 1 times 2 times 3 all the way up to P minus 1, in other words, P minus 1 factorial. In other words, if we rearrange terms on the left-hand side, we get a to the p minus 1 times p minus 1 factorial, and that is equivalent to p minus 1 factorial mod p. And now, because p is prime, the GCD of p and p minus 1 factorial is 1, so p minus 1 factorial has a multiplicative inverse mod p, and therefore we can basically cancel the p minus 1 factorials to get a to the p minus 1 is equivalent to 1 mod p. And that completes the proof. Let's now return to the Fermat primality test. Recall that this said that if we have a natural number n, we wish to determine whether or not it's prime, we compute a to the n minus 1 mod n for many random values of a less than n. Let's now consider a single value of a and see what the possibilities are. If for some value of a, we get that a to the n minus 1 is not 1 mod n, then we know right away that n must be composite. In this case, we say that the number a is a Fermat witness. It specifically demonstrates that n cannot be prime. Of course, if we get that a to the n minus 1 is equivalent to 1 mod n, then we don't know anything just yet. There are two cases. Case 1, perhaps n is prime. Case 2 is that n is composite. Unfortunately, our a was unable to detect this. So we call it a Fermat liar. At this point, we don't know, given a single value of a, if we end up in the second situation where a to the n minus 1 is 1 mod n. We have no way of knowing whether n is prime or whether we have a Fermat liar. So we do this many, many times. But how does that help? Well, it only helps if we know how common Fermat liars are. Are they a dime a dozen, or are they extremely rare? And fortunately, we know a lot about this. As before, I'm going to give you a little bit of a spoiler for this, because I really think that knowing where we're going, seeing a preview, really helps make new material seem a little less mysterious. So if we have an n and it happens to be composite, then every value of a that we choose is either going to be a Fermat witness or a Fermat liar. And basically, more than half of a's will be Fermat witnesses. Or I should say, if there is a Fermat witness, then more than half of them, of possible a's, will be them. So in other words, we have less than a 50-50 chance of getting a Fermat liar, which means that if we pick a random value of a 100 times and we get Fermat liars 100 times in a row, then the chances of just getting unlucky and the number being composite is less than 1/2 to the 100, which is astronomically small. Although what I said is not entirely true. There's one annoying case we have to deal with. Specifically, I did say if we have a Fermat witness, and it's possible that we don't. Okay, I'm getting ahead of myself. Let's go back a few steps. Here's the actual lemma that I'm talking about. If a composite number n has a Fermat witness, then at least half of all numbers a that are relatively prime to n are Fermat witnesses. Okay, how do we prove this? By assumption, n has a Fermat witness. At least one of them. So let's just take one of them and call it A. Now let's take a Fermat liar B. First, I claim, let me write this down, that in this case, A times B is a Fermat witness. So how does this help? So suppose we got a bunch of liars. So we have B1 as a Fermat liar, B2, B3, all the way up to BK. Then this tells us that the following are witnesses. A times B1, A times B2, A times B3, all the way up to A times BK. So in other words, every liar corresponds with a witness. Now we still have to claim or show that all of these are distinct, but that's immediate from the fact that the GCD of A and N is equal to 1. So that implies that A inverse exists. So A inverse exists. So in other words, if A times BI equals A times BJ, then we can multiply by A inverse and get that BI equals BJ. So this is the game. We just got to show that if A is a Fermat witness and B is a Fermat liar, then AB is a Fermat witness as well. Okay, as a reminder, we are working modulo n, and we are trying to show that AB is a Fermat witness, which means if we raise it to the n minus 1 power, we get something that is not equal to 1 mod n. So AB to the n minus 1 is A to the n minus 1 times B to the n minus 1. Now, A is a Fermat witness, which means A to the n minus 1 is not equal to 1. And B is a Fermat liar, so that means that B to the n minus 1, a Fermat liar, raised to the n minus 1 is equal to 1. So we have something that's not 1 times something that is 1. So mod n, we can just ignore the B to the n minus 1 and get A to the n minus 1. So we get A to the n minus 1, but since A is a Fermat witness, we know that that means that A to the n minus 1 is not 1 mod n, and that's exactly what we wanted to show. In other words, every Fermat liar has a corresponding Fermat witness AB, and I didn't write this down, but because A has a multiplicative inverse mod n, all of the A times B's for Fermat liars are distinct. So that means that there's at least as many Fermat witnesses as there are Fermat liars, because there might be other Fermat witnesses like A that maybe don't have this form. To summarize, we just saw how if N has a Fermat witness, then it has many Fermat witnesses. And specifically, I mean, if there's a Fermat witness, then at least half of the numbers relatively prime to N are Fermat witnesses. So that means that it's a pretty safe bet that if we compute A to the n minus 1 many times, like 100 times, and we always get 1 mod n, that our number is indeed prime. Because the chances of getting a Fermat liar 100 times in a row are astronomically small. That is, assuming that n actually has a Fermat witness to begin with. And that is something that we have to check. We have to ask, is it possible that n is composite but has no Fermat witness? In other words, if we pick any number relatively prime to n, it will be a Fermat liar. Unfortunately, the answer is yes. But fortunately, this is also very rare. It brings us to the definition of a Carmichael number, which is a composite number n for which a to the n minus 1 is equivalent to 1 mod n for all a relatively prime to n. In other words, everything relatively prime to n is a Fermat liar. The first few Carmichael numbers are the following: 561, 1105, 1729, 2465, 2821, 6601, 8911. That's not very many of them. You know, the first 89,000 possible numbers, there's only 7. For 100-digit numbers, which is still less than we're dealing with RSA, less than 1 in 10 to the 30 are Carmichael numbers. To give you a context of how big or how small this is, the number of grains of sand in all of the world's beaches is roughly 10 to the 21. The number of stars in the observable universe is around 10 to the 24. The number of atoms in a mole is, remember, 6 times 10 to the 23. And the number of atoms in the human body is less than 10 to the 28. And so to get to 10 to the 30, I think it's been estimated that the number of bacterial cells on Earth is in that range. So you're basically not going to get a Carmichael number by accident. I don't care how many millions of people in the world are doing RSA transactions and signing into websites. It's not going to happen. For 200-digit numbers, of course, the chances are even less, a lot less. The takeaway message from all of this is that if we randomly choose a 200-digit number, then it is not going to be a Carmichael number. The chances are much, much less than 1 in 10 to the 30, because that's a 100-digit number. So if we take a 200-digit number and we test 100 different values of a that are relatively prime to n without getting a Fermat witness, in other words, if a to the n minus 1 is equivalent to 1 mod n for all of these things, then we can be almost certain that n is prime. And by almost certain, I mean less than the chances of it not being prime, of getting Fermat liars each of those times, is less than 1/2 to the 100, and that is approximately 7.9 times 10 to the negative 31. Let's now describe the Fermat Primality Test with pseudocode as an algorithm. The input is an integer n greater than 0. And let's define a Boolean flag is composite to be false. So for I from 1 to 100, we're going to do the following. We will pick a random number ai relatively prime to n. And if ai to the n minus 1 is not equivalent to 1 mod n, in other words, if ai is a Fermat witness, we set the is composite flag to true, and we end this loop. Once that loop is done, we check the is composite flag. If it is false, then we print that the chances that n is composite is less than 1 in 2 to the 100, which is approximately 10 to the 30. And emphasize less, because it's a lot less than that. Otherwise, if is composite is true, then we can output that n is composite. Okay, we are now about a half hour into this lecture, and now that we finally know how to actually generate and compute with large primes, we can turn our attention to why the RSA encryption and decryption functions actually work the way they do. Here's the theorem that tells us that RSA works. Let's go through it step by step. First, n is p times q. I didn't write it, but those are both prime. And then E times D is equivalent to 1 mod P minus 1 times Q minus 1, which I'm going to write as phi of n like we did in the previous lecture. This is Euler's totient. It's the number of integers less than n relatively prime to it, and it's equal to P minus 1 times Q minus 1 for a number that's the product of two primes. Okay, now built in here, I don't have that the GCD of E and phi of n is 1, but that has to be the case because E has a multiplicative inverse, mod phi of n. E times D is equivalent to 1. Next, suppose that we have a message, m, which is an integer less than n, relatively prime to it. In other words, it's not a multiple of p or q. And set C to be equal to m to the e mod n. So C is the ciphertext. It's the encrypted message. In other words, if we start with m and we encrypt, we get m to the e, which is equal to C. Then I claim that to decrypt, to go backwards, all we have to do is take this C and raise it to the D. In other words, m to the e times D is equivalent to m mod n. And there it is. C to the D is equivalent to m mod n. Let's prove this. First, we need a technical lemma. Specifically, we'll show that m to the p minus 1 q minus 1 is equivalent to 1 mod n. Let's not worry too much about how we're going to use this. Let's just focus on proving it first. Let me start out by pointing out that because m and n are relatively prime, that means they share no prime factors. And since n is equal to p times q, that means that neither p nor q divide m. So of course, that means that neither p nor q divide any power of m as well. So I will start out by taking m to the q minus 1 power, which is relatively prime to p, and applying Fermat's little theorem. So that tells us that m to the q minus 1 to the p minus 1 is equivalent to 1 mod p. Direct application of Fermat's little theorem to m to the q minus 1 and p. And of course, we're doing this because this is m to the p minus 1 q minus 1. So we just showed that this number, m to the p minus 1 q minus 1, is equivalent to 1 mod p, and of course by the same argument, but using p minus 1 instead of q minus 1, we get the same thing except mod q. So similarly, m to the p minus 1 to the q minus 1 is equivalent to 1 mod q. This means that for some integers k and l, m to the p minus 1 q minus 1 being equivalent to 1 mod p is equal to 1 plus k times p. So it's 1 more than some multiple of p. This means that for some integers k and l, this number m to the p minus 1 q minus 1, recall that number is equivalent to 1 mod p and 1 mod q. Therefore, it is equal to 1 plus kp for some integer k and 1 plus lq for some integer q. So now, look at this equation and subtract 1 from all three sides. So if we subtract 1 from all three sides, we get m to the p minus 1 q minus 1 minus 1, and then the 1's cancel. And we get that m to the p minus 1 q minus 1 minus 1 is a multiple of p and a multiple of q, because it's equal to k times p and it's equal to L times q. And that means that m to the p minus 1 q minus 1 minus 1 is some integer b times pq. Now if we take this equation and if we reduce it modulo n, so let's do that. So let's do mod n. Recall n is equal to p times q, so that makes the right-hand side 0. So now we have m to the p minus 1 q minus 1 minus 1 is equivalent to 0 mod n, and that is exactly what we wanted to show in the beginning. So that completes the proof. At last, we can turn our attention back to the theorem at hand, which is why RSA actually works. Let's take a few moments to recall what we were trying to show. So M is a message, and to encrypt it, we raise it to the eth power, and we call that the ciphertext C. Everything is mod n. And then the claim is that if we want to decrypt that, we just raise that to the dth power, so C to the D, which is M to the ED, that is equivalent to M, the original message, mod n. So in other words, that exponentiation to the dth power is the inverse of exponentiation to the eth power. So writing that down here, we need to show that m to the ed is equivalent to m mod n. And what we know, what we just proved, is that m to the p minus 1 q minus 1 is equivalent to 1 mod n. So somehow we're going to use this fact from the lemma to prove the claim in the theorem. And let's just remind ourselves that this is equal to C to the D, the decrypted version of the ciphertext, which is the encrypted message. Okay, do you got that? Let's write it down for good. We know that C to the D is equivalent to M to the ED mod n, and we need to show that it's also equivalent to M mod n. In other words, it suffices to show that M to the ED is equivalent to M mod n. Okay, let's recall what E times D is. So we don't know what they are, but we know that their product is 1 mod P minus 1 Q minus 1. So let's write that down. So we have that ED is equivalent to 1 mod P minus 1 Q minus 1. And that means that ED is equal to 1 more than some multiple of P minus 1 Q minus 1. In other words, ED is equal to 1 plus J times P minus 1 Q minus 1 for some integer J. Now here's what we're going to do. We're going to take this last equation. ED is equal to 1 plus J, P minus 1, Q minus 1, and we will exponentiate. How do I want to say this? We'll take M and raise it to both the left-hand side and the right-hand side. So M to the ED is equal to M to the 1 plus J, P minus 1, Q minus 1. And that's where we're going to apply our lemma right here to the right-hand side. In other words, M to the ED is M to the 1 plus J, P minus 1, Q minus 1. Now we just use laws of exponents. We can write this as M times M to the J, P minus 1, Q minus 1. You see where I'm going with this? That last part is going to be equivalent to 1 mod n. So this is M times M to the P minus 1, Q minus 1. that whole thing raised to the j, but it doesn't matter because that whole thing is equivalent to 1 by the lemma above. So this entire piece we can just ignore because it's equivalent to 1. And there we go. M to the ed is equivalent to m times 1, and that is equivalent to m mod n. That completes the proof of the theorem, and that is why RSA works. And I think we're going to leave it there.